MagLab presents Take 2 series marker.
Hi Thomas, welcome to the MagLab.
It's great to be here.
So can you tell me a little bit about the research that you're doing here at the MagLab?
Sure, so we're here to apply magnetic fields to layered materials.
Layered materials, can you tell me a little bit about that?
Sure, when we talk about layered materials, what we're referencing is the way the atoms are arranged inside the material. So the atoms are very tightly bound into sheets or layers, but these layers themselves are very weakly coupled to each other, so they're easy to separate.
So the weak binding, is that valuable or is that important to the research that you do and how the sheets move?
It's important in many different ways. So one way in which it's important is that we can actually prepare the atoms in a single atomic layer. So this is somewhat unusual because we usually don't think about a material as being a single atomic sheet.
What kind of materials are you looking at?
So we look at a great variety of elements from the periodic table that through either nature or synthesis in a lab can be prepared in a layered form. So one of these is in fact tin selenide. And this is an interesting material because of its thermoelectric property, which is to say how heat and electricity couple together.
Yeah. Are there any exciting projects that you're working on besides obviously the one here at the MagLab?
Yes, so actually some of my students are working on using layered materials to make large transistors that are sensitive to what's inside your water. So it's important for water quality monitoring.
Oh, that's excellent. Oh, well, that's it. That's the bell. Thank you so much, Thomas, for talking to me today.
It was my pleasure.
MagLab presents Take 2 series marker.
Good afternoon, Thomas.
Good afternoon, William.
So you're running an SCM2 today. How's it going for you?
It's going great. We're measuring magnetoresistance and Hall resistance in new 2D materials.
Okay. And things are quiet and things are happy.
They are suitably quiet, and that's actually what motivates some of our interest in 2D materials. We like them because they have no dangling bonds on the surfaces. And that's one of the things that makes them very interesting for making transistors, for example, because that absence of dangling bonds reduces trap state density, and you get better transistor characteristics.
Okay, so you're doing very fundamental work with the material itself, not necessarily caring how the transistor is going to stack up together.
Indeed, because the starting point is to understand the material that you will work with to make an electronic device. And so silicon, which we use in transistors today, is very well studied, but these new materials, relatively little is known. We don't even know the band structure in many cases.
Right, and that's very important.
Indeed.
So how does this compare with, say, graphene, which is very well known?
So graphene is the prototypical 2D material that got people to look and revisit many of the other 2D materials that are out there. So graphene's band structure is very well known, and we know how to manipulate it through strain and other effects. But in the case of tin selenide, which we're working with right now, the band structure is still not fully mapped out. So that's what we're here to do.
Excellent. And so if you'd like more information about Thomas's work, we send you to the link on the screen.